Hey everyone, and welcome back. This is CybergonCTF 2023, hosted by Cybergon. It's a company based out of Myanmar, and today I'll be covering a couple of the Pwn challenges, specifically the first four. Couldn't get the last one. I feel like I'm at the last stage, but I'm missing a libc leak and I just can't find it. But anyways, let's get started. This is Pwn Teeny. It's small enough to be powerful. We're given a netcat port and a download file. So if you know the trick to this one, it was a very simple challenge, or a relatively simple challenge. If you don't know the trick, it was probably impossible. And the trick for this challenge was doing a SIGROP. So we have a very constrained binary here. There's only one function, the start function, and it's just going to do a read sys call with 500 bytes, and then return. And that's pretty much it. If we look down below, we can see there's two more bytes here. If you press D on Ghidra to decompile it, we can see we get a pop rex or RAX and then a ret. So the authors left us one extra gadget. Like I said, but this is pretty much all we get. And also at the very bottom of the binary, they also define a string bin shell, which we'll need later. So when you're in these constrained environments, usually it means we're going to be doing a SIGROP. And if you're not familiar with SIGROP, basically it is a sys call that allows you to store a bunch of stuff on the stack, and then the kernel will populate the CPU registers based off of those values on the stack. So since we have a large buffer overflow, what we're going to do is we're going to overflow, we're going to start wrapping so that we can set everything up for a sig return. Specifically, all we have to do is set RAX equal to 15. And then from there, we're just going to populate the stack with all the register values we want. Thankfully, Pwn Tools makes this very easy. You basically just fill out the structure. We put that on the stack. We call sig return. All of our registers are populated. That includes the RIP register. So we're going to point RIP register back at a syscall. And from there, and we'll set up bin shell in RDI. We're going to be calling execve, which is 59 right here. So we're going to set RDI to bin shell, and then we're going to leave these as null, and that's it. To see what the salt script looks like, we're just doing standard Pwn tools. We're going to, from here we need to figure out where we're going to start wrapping from. One way to do this is to use Pwn cyclic. So the very first thing I did is I did a GDB attach. I send p.sendLine, Pwn cyclic 50. I just send 50, and then do an interactive. And that way, let me close out of this. When we run the script, we can see where the process crashes, and we know that's how many bytes we need before we can start wrapping. So GDB is started, I hit continue, and we can see we hit a sig vault. And if we look at where it is, RIP is right here. It's trying to do a return, so it's going to pop the first value off the stack, and the first value off the stack is CAAA. So we comment this out. We say the ret offset starts at CAAA, and I think this is just 8 or 16. So it was there. No, 8, sorry, because it's AAA, BAA, CA, so 8. Then we calculate the address of bin bash. To get this, there's a bunch of ways. You can just do search bin and see what happens. And so we can see in Teeny, there's at this address, there's the string bin bash. You need to subtract 1 because you need that initial slash, so 40238. So we have the address of bin shell. Then we need the syscall address. You can get this from Ghidra or anywhere, so 40015, the address for syscall. This is how we define a SIGROP frame in Pwn Tools. So sig return frame, this is 59 for RAX. This is the syscall for execve. We want the bin shell to be called, so we set that into RDI. We clear out the other two, and then RIP should be the syscall because we want it to jump straight back to the syscall after it's done SIGROPing. Then we kick off the SIGROP. We're going to do that by just wrapping. The only thing we need to do is we need to set RAX equal to 15 because we're calling syscall 15. 15, otherwise sig return doesn't expect anything, which makes it such a beautiful gadget. Oops. So we're going to set RX to 15 and then jump there, and that's pretty much it. We send enough filler bytes so we get to the ROP, start of the ROP chain, and then from there we send our ROP chain and then the frame for the SIGROP, and we're good. We can just run it on remote. Get rid of this, get rid of this. Python 3 solve. I do ls, and there we are. Cat flag.txt. It says CybergonCTF sudo ROP chain. So fun. This is Pwn really random. It says if you can guess, you win the lottery. We're given a netcat port and a download file. If we open up the download file in Ghidra, a couple things to note. There's only 3 or 4 functions. One of those functions is called potato, and we can see we have a win function here. It's just going to call system bin shell. So we have our target, some sort of ret to win. If we take a look at the protections real quick, we can see there's no canary and there's no pi. So we don't need an info leak, and most likely we're going to be doing some sort of buffer overflow. So it kind of seems like we have a ret to win sort of challenge. If we start going through the main function, We have some signaling, some alarm, some setup. It's going to ask us for our name, and then it's going to do a scanf on this in buffer. I just type L so I can rename variables. If we look at this data thing, you double click it, we can see it's a %s. So that means we have a unbounded buffer overflow. Let's do data terminated C strings just so it shows up here. Already we have a buffer overflow. From there, it's going to seed random. It's going to generate a bunch of random values. It's going to do some math on those random values. Then it's going to save them. And then we need to guess those numbers. If we guess them, all 10 of them, we'll get a return 0. Otherwise, we're going to get an exit. So I think with all that, we can make a game plan. And the game plan is we're going to use this initial buffer overflow to ROP, or really just return to win. So we'll put that potato win function at the end, and as long as we can guess the random numbers, it'll call return 0, and we'll be able to spawn shell. So 2 little details. First off, somehow we need to guess these random numbers, and it looks like it's being seeded by local 18, which is they call it a rand. But thankfully, as part of our buffer overflow, it'll be at a constant value every time, or we can set a constant seed value because this is part of our buffer overflow. So that makes that easy. Then we need to calculate what all these values are. You can go through the RC function and like try to calculate it because, you know, you can do like the C types foreign function interface or whatever. And but it's easier just to run the program with a known seed and then just see what that output is, because that output will always be the same. And then we'll just send those raw values. And that's pretty much it. So just take a look at the solve script. This is really random. We do a bunch of imports and stuff. Let me, do the local one first. So the very first thing I did was a pwn cyclic, just to figure out where all the offsets are. So I found out that they're seeding random from this offset. So if we wanted to send a different value, we could. I just ended up sending pwn cyclic, so it really doesn't matter, but it is there. We also saw the seed. This is the seed that's being sent. Again, originally I was calculating the values. We don't actually need these anymore. Then we figure out where the return offset is. This is where the ROPing will start at this address. And then I just stored the address of one ret statement. I'm guessing it's probably the one right here. This ret, we need it because some libc alignment issues, which I'll talk about a little bit later. But yeah, so to start out with, first thing we do is we actually overflow and do our buffer overflow. So we're going to send enough bytes so that we get to the return offset. Then at the return offset, we are going to ROP. First, we're going to do a ret for stack alignment. Newer versions of libc require that the stack is aligned so the RSP ends in a 0. When we do this, it wasn't aligned, so you just add an extra ret there so the stack gets kicked back by 8 bytes. So that way when it calls our win function, everything will be aligned correctly. From there, we're going to send those values that random calculates. To figure out what these are, you can just run the challenge in GDB and see what the values are that we need to send. So if we do this, we can jump right after all the values are calculated. So guess my number. So let's stop right here. Somewhere like right here, I'll do make Ubuntu 22, Python 3 solve in my local GDB, tmux. Cool, it generated a bunch of numbers. If we do examine, let's say 20x at the variable v, we can see it is not filled out. Maybe it's filled out now. There we go. Now it's filled out. I forgot to hit continue. But we can see we can just grab the values. These are the values that are calculated and that we need to send back. You can see a lot of them are negative, which was a little bit tricky, or they're at least sign extended. So you just copy out these 10 values or whatever, load them into the challenge here, and we send them over. And yeah, after that, we'll get the return statement, and we should just win. So we'll hit continue, and we can see that user bin dash, which has just been bash, has spawned, and we have shell. So we can try running it on the remote host. Get rid of this, get rid of this. Python 3 solve, we connect, blah, blah, blah. There we go, ls, and there's the flag. CybergonCTF, not really random. This is pwn autograph. It says, let me collect your autograph for the CTF. We're given a netcat port and a download file. If we open it up in Ghidra, here's the main function. It's going to do some setup. It's going to call a menu function. In the menu function, there are 3 options, but if we look below, it's going to have those 3 options. But if we supply a 9, there's this sneaky debug notes function. If we look at the debug notes function, I'm just typing L so I can rename it. Enter your notes. It's going to read 256 bytes into this buffer. It's going to puts, and then it's going to printf our buffer. So a printf on raw input that we control is pretty much game over. So we're just going to be doing some printf exploitation. Specifically, we're going to be doing a couple different steps. First, let's look at the protections enabled. So let's do checksec, file, autograph. We can see that there's no canary, so we could be doing a buffer overflow, but we don't care since we have printf. That's more than enough. NX, we're not going to be writing shellcode, so we don't really care about this. Pi is enabled, so we might need an info leak. And it turns out we will need an info leak for the main elf section, just so we can leak some stuff for libc to figure out the correct libc version. But yeah, since we have a printf, that's all we need to completely own this binary. So we're going to do this in a couple of different steps. First thing first, we need to figure out the address of the main elf. Since pi is enabled, that's going to be floating all over the place. And the reason we want that is so that we can start leaking global offset table values. libc wasn't given as part of this CTF, so we don't know what libc version they're using, and we're going to be doing some sort of return to libc sort of exploit, or we're going to be calling system within libc, so we need to know those what version of libc they're using and have a libc leak. So like I said, we're going to leak the main elf so that we can start leaking global offset table values. And then from there, we're going to overwrite one of the global offset table entries with, and just replace, I think replace string copy with system. And so that way, when we do a string copy call later, it'll call system instead with our payload and we get shell. To see what that looks like, this is my solve script. So all very standard stuff. We don't know what libc version is yet. I'm going to show how to calculate this. We're connecting to remote. So first thing first, we connect to the server, we send choice 9, so we're in the printf menu. From there, we can send our notes. The first note we're going to send is $34$p, so leak the 34th value off of the stack. This happens to be the an elf leak. I don't know what it is, but it's some value. And once we have this, we can calculate the base of the elf. I had to run through a bunch of values to find one that was consistent both locally and remote. To do that, I use a little line like this. This is just going to print out all values from 30 to 40. So first I go from 0 to 10, 10 to 20, 20 to 30. And it just prints out the number, and then it does the format so I can just see which number looks good. From there, we have a elf leak. So step 1 done. Like I said, we need to figure out what libc they're using remotely. And so to do that, I leak values off the global offset table. So again, very standard printf stuff. We're just going to leak a couple of values. We use the %s format string modifier to leak values because that takes a pointer. So we're going to send it a pointer of the global offset table entry and ask it to print the string there, and that'll print out those table entries. We're going to leak table entries for puts, printf, and alarm. Once you do that, you can go to a libc database. So you'd put in prints and printf and alarm, blah blah blah. Oops. You'd put those in, and that'll tell you which specific version of libc they're using, and you can also download it. And so I downloaded it, and here it is right here. So now we're using the same libc that remote is using. Cool. From there, we need to overwrite one of the global offset table entries. Oh, and from here, we also get the libc leak. And so we can calculate the base address. And so now we know where libc is. And from there, now we just need to overwrite something and call system. If we look at choice 1, so let's go back to main, menu. I think I used add note. Yeah. So if you add a note, you can do a note here. It'll ask for a note. It'll read it, and then it'll copy it into this note variable. So it's going to do string copy note. This is what I used as my system target. So I'm going to overwrite string copy with system, so that way it'll call system on note. And we just assign note beforehand to bin shell. So then it'll just be system bin shell. So the first thing I do is I set that note to bin shell. So I just say add a note, set that note to bin shell. And then I'm going to do another printf, very standard printf sort of stuff. We're going to overwrite the global offset table entry for string copy with the system symbol within libc. To do that, we just do a format string payload. It's offset 6. To calculate that, let me just run it real quick. We're 9. You can do 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, sorry, 8. Then we do %p, oops, p. And we can see that it is offset number 1, 2, 3, 4, 5, 6. So the 6th offset on the stack is our A's. So if we were to set an address here, then we could do something sneaky at this offset. So offset 6, we set that there. We pass it our writes. So we're overwriting string copy with system, and then we do write size. I just do shorts. You can do bytes. You can do whatever you want. Cool. So we'll do that. We'll go back to option 9. We'll do that printf exploit, and then from there we'll go back and call the string copy, which is now system, and we should get shell. So let's do Python 3, solve.py. It should be on remote. It is. Cool. We're leaking values. We're doing the printf exploits. There's the big overwrite, and let's see where we are. And there's flag. It says CybergonCTF, format string is dangerous. Cool. This is Pwn Notebook. It says write your own destination. We're given a netcat port and a download file. So this one was a relatively easy heap exploit challenge, and they made it easy for a couple different reasons. We go to main. It's going to print out a little menu. Our menu options are add note, edit note, view notes, and exits. What makes this challenge easy, or they were very generous, is that in the add note, they actually malloc twice, and the first malloc chunk contains a pointer to the next one. And why that makes things relatively easy, I'll explain in a second. The second bug, and both of those chunks are 8 bytes. In the edit function, we have our overwrite, and here it's going to take in one of those nodes and overwrite it with 256 bytes. So we have a huge buffer overflow. So we have a overflow in the heap, and the heap has a bunch of pointers that we can mangle to point to different things that we want. And as part of that, we also, obviously we have an edit function, so we can get it to point to somewhere. So we have an arbitrary write, and there's also a view function somewhere, so we have an arbitrary read. Nice and simple heap. Like I said, we can control these pointers, and we can get them to point anywhere, and then we can read anywhere, and we can write anywhere. So we basically have full control. There is a win function, but the win function says not today, so we don't get that. So not too bad. This is the solve script. I asked the challenge authors as part of the last challenge if they were giving us libc. I didn't say anything. Maybe I missed a message. They said they weren't, which is fine, but they also said that they were using the same base image for all the challenges. And so because of that, I just copied libc from the previous challenge since I already had it laying around. So we know what libc they're using. First thing first, I create 2 nodes. Actually, a very useful tool for doing these heap exploitation challenges. Make a Ubuntu 22, just to make sure everyone's aware of it. We're going to do gdb notebook. We're going to run. Let's add a note, index 0, contents, a bunch of A's. Let's add a note, index 1, content, a bunch of B's. I'm going to hit cancel. There's a function called viz heap chunks. This thing is amazing. And so what's going to happen here is this is our first chunk. We can see, and they're color coded, so we can see this is the size and the metadata. We can see this is a address 15F52C0, and it is pointing here. So this is the first malloc chunk that was created, and it's a pointer to the next one. And then we have one here that's pointed to here. I inserted an extra A. You should ignore that. There should only be 2, but that's just because I put in too much content. So like I said, since we're going to start doing buffer overflows, let me actually just redo this. Run, one note. Do index 0, A's, and then we'll add a note, index 1, B, viz heap chunks. We can edit this stuff right here. And so what we're going to do is we're going to overflow this with the edit function all the way to here. And so we're going to overflow this address and have it point somewhere cool. And the first cool spot that we're going to leak is we're going to point it at the global offset table. And we're going to do that so that we can start leaking libc values. So we'll point it at some global offset table entry, and then we'll do view chunks. And so instead of printing out the contents of this, because right now this points to here, it'll print out, the address of puts or something. So we have our libc leak. Then we're going to do that same buffer overflow. We're going to overflow from here. So we're going to call edit on this chunk. And instead, we're going to point this to, actually, I think we point it to a different global offset table entries. And what we're going to do is we're just going to write a 1 gadget there. I think I point it to exit, and so that way when exit is called, instead of exiting the process, it'll just call 1 gadget, and we should get shell. So really not too bad. This is what the solution looks like. So like I said, same version of libc. We're going to create 2 notes, so we can do that overflow. So we're going to do that first buffer overflow. We're going to edit the contents of A. I'm just going to send a whole bunch of A's. We're going to keep the consistent metadata. It was OX21, OX21. And then we're going to put in the address of puts. So cool. We have the puts address. After that, we're going to use the leak function. The leak function will just give us that address. I mean, we can call it now. Is it 3? Yeah, you can see it's just printing out contents. When we do it in the solve script, obviously we'll get the address of puts. We parse that out. We now have the base of libc. Cool. From there, we just calculate the 1 gadgets. Calculating 1. If you haven't seen 1 gadgets before, oh my gosh, they're amazing. Basically, just do 1 gadget and you pass it in a libc version. And if you're able to match these constraints and jump to this address, this is from the base of libc, it'll just call bin shell for you. So cool. So we copy out a bunch of 1 gadgets, and I just test all of them. So we overwrite return, and then from there, we're going to overwrite that global offset table entry, and then we just call exit. And if everything works well, we should get a shell. I think most of them didn't work, but the last one worked. So that's the one I ended up using. I usually just put it into an array, and then I just, or for one gadget, and then I just cycle through them. So I did 0, 1, 2, and 3 thankfully worked. Yeah, so Python 3, solve that pi. Doing a bunch of overflows and leaks. Let's do an ls and cat flag. And we get CyberGon heap with leak. And that is all the challenges I was able to solve. I spent a bit of time on Tor. I just can't push it over. I can do arbitrary jumps. I'm just missing a leak somewhere. But yeah, fun challenges. Thanks CyberGon for hosting, and I will see you at the next CTF. Cheers.